Welcome, Calculus 2 students. Today we are looking at applications of differential equations, and first on the agenda are population models. Now, we've looked at population models previously. We have looked at both exponential and logistic growth population functions. Let's note that in a logistic model we have a carrying capacity K, and with the exponential model our population continues to grow exponentially. And if we look at the derivatives of these, we note how the rate of the population is changing with time. So let's look at an example. In example 1, we have a prairie dog logistic model. I plug in what I know so far, and this 200 is my carrying capacity, so I plug it into my logistic growth formula. Now my problem is to find that initial population equation. So what I'm going to do first is I'm going to write this as dp over dt. Now we have solved one similar to this in 8.3, so I'll go through this again but fairly quickly, and we're just going to write this as rp1 minus p over 200. Then what I'm going to do is separation of variables. After my separation of variables, I will then do partial fraction decomposition to find what this left-hand side integral becomes. After integrating and doing a little bit of algebra, this is what I get, and then I'm going to take and do this to both sides, and with some manipulation I will then get, with a little more algebra, I get this population function. Now what I'm going to do is plug in one of the points I know, which is p of 0. It is at the original time that we started counting. That population was 8, and then I'm going to solve for c. I get that c is 24. Now I'm going to rewrite and write down my population equation. So that population equation is then p of t is 200 over 1 plus 24 e to the minus rt. Next thing I need to do is get that rate, that r, and I have another point, and that point is 10 years, 200 dogs, and I'll plug that in and get my r. Alright, this becomes my logistic population equation, and it has a carrying capacity of 200, meaning that as time goes on and on, that our population approaches 200 and stays kind of steady there. In this next example, we're looking at models of tumor growth, and we see that when we graph our rate of growth, it is very similar to that of the logistic model. It's just skewed slightly, and its maximum changes a bit. But it is just a form of a logistic model, so we're going to expect that it has a carrying capacity as the regular logistic model does. So the A, we have discussed the features. Next we're going to find the general solution, which means that I will be doing a separation of variables. So I'm going to write this down, separating variables, and then integrate as we did previously in the other example. After separation of variables, note that this guy here can then be integrated using a u equals, we're going to let u equal natural log of m over k, and then this means that du is going to be equal to, and I will take the derivative of the outside, so it's just going to be a u prime over u, so that's going to be 1 over k over the m over k, and what I end up with here is just going to be the 1 over m. Oops, and I forgot my dm. Alright, so let's make note that there is my du, so I'm going to have integral of du over, and u is just this deal, so it's just du over u. That's pretty handy. Alright, so this is minus rt plus c. Alright, and then I'll rewrite in terms of m. Alright, I have this natural log of the natural log, so I'm going to exponentiate both sides and then relabel my e to the c. I still have a natural log in terms of m, so I'm going to exponentiate both sides again. Alright, whoops, in rewriting, I'm going to have m of t equals k, and this is pretty ugly, e to the c, e to the minus rt. I'm going to use my initial condition. My initial condition is just that m of 0 equals m naught, and this will have me, if I plug this in, I'll get the m naught equals k e to the c, and solving for c, I'll get that c equals the natural log of m naught over k. Therefore, when I plug this in and do a little bit of algebra, I'll get m of t is k times m naught over k, all raised to the e to the minus rt power, which is pretty ugly. When you graph this, you will get what is a logistic growth curve with that steady state of m equals 10 for our particular example. In our stirred tank problem, we have a solution, and we are putting in something that is going to be thoroughly stirred and thoroughly mixed throughout, and it will be our concentration of this substance in our solution, and we are to assume it to be uniform, and our concentration is changing over time, and our goal is to find the mass of the substance that we're putting in there at all times. So in example 3, they want us to find the mass of the salt in the tank at all times. So what we've been given at first is we've been given that initial mass, and that initial mass is the fact that we have 1,000 liter tank and our initial concentration of 5 grams per liter. So 5 grams per liter gives us 5,000 grams. We need to know our initial concentration, and they give that to us as 25 grams per liter. And we also need to know our inflow rate, and they give us that. Our inflow rate is R is 8 liters per second. So let's plug that into our mass flow equation, and then we'll see what we get. We'll have to integrate in order to get our m of t. Just plugging in the numbers that they gave me for the givens, I get m prime of t equals this. Next, what I'm going to do is I happen to know the initial point, m at time 0 is the mass at time 0 is 5,000, because I found that right here. I'm going to plug that in, and then I will solve for m of t. Alright, after doing my little algebra manipulations, I get my mass of the salt in the tank at any time t. Next, I'm to find the concentration of the solution in the tank, and I can do that by dividing the mass function by the volume in the tank. In other words, I'm just going to take the concentration and divide everything by 1,000, so that would just give me 25 minus 20 e to the minus 0.008 t. And that's the answer for B. Alright, let's look at what happens with the hare lynx models. We see that as our lynx population increases, they need more food, so they eat more hares, and the hare population goes down. Once the lynx population goes down, then the hare population starts to rise, and it keeps in this cyclic pattern over and over. And we can model that with our differential equations. First up, we're given a predator-prey model, fox hare, and we are to assume, or we are given, that our fox hare populations are these right here, and how that rate of population changes. Next, we're to find the equilibrium points of the system. This just means that we're going to find when each of these rates equals 0 and what those solutions for f and h look like. Alright, in solving these we find that we have 2 points for this to occur simultaneously, and that would be when we have 0, 0 for f and h, and I'm writing the points as f, comma h so that you'll know, or it would happen at 3, 4. So we are going to draw that in our slope field, or direction field curve. So first up, we have our slope field from part A, where we're just looking at those equilibrium points, and we're finding where both f prime and h prime are either greater than 0 or less than 0, so that we can draw those direction points, and you'll see them listed here. Next, we are to make vertical lines at the 4 and horizontal lines at the 3, and then we are going to be looking at where those equations in their entirety are greater or less than 0, and you'll see our slope fields as represented here. And then you can see what each of those lines would look like at time t for a given population of each. And that's all we have for 8.5.